All right. So now we're going to continue to finish chapter 18, one sample T problems. Last class, we talked about a one sample T confidence interval. So compared to one sample Z confidence interval, basically we use a different statistics. The reason we are doing this is because we most of the time do not know population standard deviation, and Z inferences is not practically useful because you have to know that, parameter sigma. One sample t-test, we started a little bit last class. So we talked about the calculation of t-statistic. Basically, it's very similar to a z-statistic. You replace that sigma by s, then you can have a t-statistic, right? Then, depending on what kind of alternative hypothesis you have, different signs, you can have different p-value as a t event, right? And the key thing is basically, how do we find these probabilities from the use of t-table, right? So we need to use t-table to look at these probabilities. And we started a little bit. We started about, how do we find p-values. So if we have degree of freedom equal to 9, last class we started on this. We have a one-to-one match between t-score and the probability. So when t-score is 0.703, the probability is 0.25. The t-score is 0.883, the probability will be 0.20, and then basically give you one-to-one relationship here, and the relationship is given on the top density curve. You have a t-distribution, center at 0, and 0.703. This tail probability will be 0.25, and so on, right? So then probability of t greater than 0.703 will equal to 0.25. Likewise, probability of t greater than 0.883 will equal to 0.20. So then if you want to find the probability of other events, for example, if you want to find the probability of t greater than 0.81, that will be between the probabilities of two neighbors, right? These two are the neighbors 0.81, so it will be between 0.20 and 0.25. And then if you want to find the probability of t greater than 0.5, then you can only compare with one neighbor he has, right? This is the only neighbor you have. So compared to that, it will be greater than 0.25. So another pair between t and p will be, for the 9 degree of freedom, you have t 4.781, the last t-score. The corresponding probability is 0.0005. That means probability of t greater than 4.781 equal to 0.0005. Right? The same relationship there. So then that will give us another scenario. If you look for probability of t greater than 6, then you only have one neighbor on that degree of freedom. This is the only neighbor you have, right? You compare this probability and that probability, this will be smaller than that because the larger value you have, the smaller tail you have on the t-distribution because you're looking at the right tail, right? Greater than sign. So this will be smaller than 0.0005. Okay? So in general, you only have these three scenarios to find probability from t-table. Either your t-score is very, very small, then the probability to the right of that t-score is pretty big. If your t-score is very, very big, then the probability to the right of the t-score is very, very small, right? And if your t-score is somewhere in the middle, then it will be in between the two neighbor probabilities, and that's it. Okay. And then we'll also talk about, we have some simple facts of NAT distribution. So we have a t distribution, symmetric, bell-shaped, center at 0. Then for probability of t greater than 0 will be exactly 0.5 because that's half of the whole distribution. Then probability of t greater than a negative number, doesn't matter if it's negative 1 or negative 0.5 or negative 0.7, it's going to be to the left of 0, right? So then the probability will be greater than 0.5, right? It's more than half. Then probability of t greater than 1 compared to probability of t greater than 2, this probability will be bigger. The smaller t-score, the larger the upper tail area, right? And then lastly, probability of t greater than 1 will equal to probability of t smaller than negative 1, right? So we have greater than 1 is this area, smaller than negative 1 is this area. They should be equal because they're mirror image of each other, right? Great. So with this in mind, now we're going to talk about how do we find p-values for various different scenarios in t-test. Right. So in t-test, your alternative hypothesis could have different scores, different signs, sorry. So it could have greater than sign, smaller than sign, or not equal sign, right? And based on the sign, your p-value will take different event, right? So don't forget that. Then, for example, if we have this scenario, how do we find the p-value? Okay. So let's remember this, greater than sign, sample size is 10, and p is 3.453. Bring it back. Right, so remember the three scenarios we have, right? But we need to have a greater than sign before we go to t-table. So now let's look at the first practice. So alternative hypothesis has greater than sign, sample size is 10, and t is 3.453. Right, so basically have a greater than sign. The alternative hypothesis will determine the p-value form. The p-value will be a probability of an event that we need to remember here, right? So we have a greater than sign, the p-value will take this form, right? Probability of t greater than calculated t. Then what is calculated t? This is right here, 3.453, right? Then replace it, t greater than 3.453. Okay. So then, this is a t event. We need to look up in the t table. But before I go to the t table, you need to make sure the sign is greater than sign because t table will give you the right tail, right? So make sure the sign is greater than. If it is not greater than, we need to change it into greater than before I go to t table. All right. So then we're good to go because it's greater than sign. But now we need to check the degree of freedom. So t table gives us many different t distributions. We're only going to supposed to use the t distribution that for appropriate for a problem. Okay. So in this case, degree of freedom sample size n minus 1, n is 10, degree of freedom will equal to 9, right? Then we're going to just look at the t-table with 9 degree of freedom. We'll try to match this t-score on the table. We're not able to find the exact, but we're able to find neighbors, right? You could have one neighbor if it is extreme small or extremely big, or otherwise it will be somewhere in the middle, right? Okay. So in this case, 3.453 with 9 degrees of freedom is going to be between 3.250 and 3.690, right? And the corresponding probability for these two t-scores on the table will be 0.005 and 0.0025, right? And then remember earlier we talked about we have two neighbors, the probability of the event will be in between the two probabilities, right? In between these two probabilities of the two neighbors. So we're going to write in the from small to large, the small number go on the left, the large number go on the right. That's the common, convention, right? So our p-value is going to be between 0.0025 and 0.005. Okay. Right. So that's the first practice. We're going to skip the number 2 because that's exactly the same as number 1. We're going to do the number 3. So in this case, alternative hypothesis will be mu is smaller than a value. And then the calculated t will be 3.12. No, it's negative 3.452. And then sample size will equal to 20. Right? So how do I deal with this? First, always write the p-value according to the p-value definition. So p-value will equal to, depending on your alternative hypothesis, right? Well, your alternative hypothesis has smaller than sign. So now if we go back to the p-value, when you have an alternative hypothesis smaller than sign, then your p-value will take a different form, right? The probability of t smaller than calculated t. So here we're going to write probability of t is smaller than calculated t. Then calculated t is right here. So to replace it, that'll be probability of t smaller than negative 3.45. Right? So this is a t event. We want to look it up on the t-table. But we need to make sure the sign is greater than sign before I go to the t-table, because t-table is the right tail, right? We need to have a greater than sign. And how do I convert it? Okay. So we're not going to use 1 minus like in the z-table. Now we're going to use a different rule here. We're going to use the symmetry rule. So the left tail probability will equal to the right tail corresponding probability because the t distribution is symmetric. This symmetry rule also apply in the z distribution, but because of the table layout, we have to use the symmetry rule here. Okay. So then, how do we convert this? Very similar, right? We're going to convert the sign from smaller than to greater than. At the same time, we're going to convert the number sign from negative to positive. Okay? So now you have greater than a positive number. Right? Then we can look up the t-table because the sign is greater than sign, which is consistent. Then don't forget, we need to check the degree of freedom. The degree of freedom will be n minus 1. N is 20 minus 1 is 19. Okay? So then we check 19 degree of freedom. Look for 3.452 on that row. 19 degree of freedom, 3.452. That will be between 3.174 and 3.579. And the corresponding probability for each of these two will be on top 0.0025 and 0.001. Right? Then, just like the one above, right? If your t-score is in between the two neighbors, the probability to the right of the t-score will be in between the two probabilities of the two neighbors, right? You write it in a small to large, right? So this will be the probability of t greater than positive 3.452, which is our p-value, right? Okay. So now let's look at another practice. So for number 4, alternative hypothesis is still smaller than sign. Then sample size n will equal to 18, and t-score calculated to be 2.123. Right? So here, what is the p-value? The p-value will equal to probability of the same as this, right? You have smaller than sign, gonna have the same p-value form, t smaller than calculated t, right? Then we're gonna bring in the calculated t here, that'll be probability of t greater than, not greater than, sorry. You need to be smaller than. T smaller than positive 2.123, right? So then here, we need to look at the t table because this is t event, but the sign is not consistent. So we need to convert it using the rule here, right? So that will be probability of t, change the sign from smaller than to greater than, and change the number sign from positive to negative, right? So now it's consistent with t table. But now if you look at this probability, do we even need to look up the t table? We know for any t distribution, regardless what degree of freedom we have, probability of t greater than a negative number is always going to be more than a half, right? So we don't have to look up the t table in this case. It will be always greater than a half, right? So it's a very, very big probability. If p-value is big, then you're not going to reject it all, right? Now let's look at the last two practice. They're very similar to each other. It's just a small difference in the sign. So number 5, now the alternative hypothesis is mu is not equal to a value. So the sign is unequal, right? The sample size will be equal to 20, and the calculated t will equal to 3.234. Okay. So first, we need to write the p-value form. What will be the p-value form when the alternative hypothesis is unequal? So if you don't remember, let's go back to here, right? So 2 times probability of t greater than calculated t's absolute value. So just copy it. 2 times probability of t greater than calculated t's absolute value. Then the calculated t is right here. We'll bring them in. That'll be 2 times probability of t greater than 3.234, take absolute value. And we know how absolute value function work, right? It would just basically keep everything as positive, right? So absolute value of positive 3.234 will be just positive 3.234, right? Then this is a probability in regard to t-score, so we can look it up from t-table, right? Then we want to make sure the sign is consistent. In this case, it is. We want to have a greater than sign, right? Then we can look up the t-table, but don't forget to check the degree of freedom. That will be sample size n20 minus 1, which is 19, right? So we're going to look at 19 degree of freedom, then probability of t greater than 3.234. This is what we can look at, right? With 19 degree of freedom, 3.234 will be between 0.0025 and 0.001. So basically, that will be the two probabilities, right? I didn't give you the t-score. The t-score will be corresponding to 3.197, and the t-score here will be 3.611. Right? Is that right? No, it's not. 3.174 and 3.579. It's very easy to look up lines. 3.174 and 3.579. But the t-score doesn't really matter much. You need to match with the probability on top, with the two t-scores of neighbors, right? So then probability of t greater than 3.234, we know that will be between the two probabilities here, 0.001 and 0.0025, right? But the problem is here, we're not done yet. This is not our p-value, right? Our p-value will be twice as big, right? Will be twice as big as this probability, right? So then we need to multiply by 2 on each side on the inequality. Then the middle part will become our p-value. That will be between 0.002 and 0.005. So this is our p-value. It's a pretty small probability. Right. So now let's look at the last scenario. So alternative hypothesis is still unequal. Sample size will be still 20. And now calculate t will be a negative number, negative 2.768. So first, we'll write the p-value out. The p-value by definition will be 2 times probability of t greater than calculated t's absolute value, right? The same as the previous question. And then calculated t, plug it in, will be 2 times probability of t greater than negative 2.768. Take absolute value, right? So don't forget about that absolute value, otherwise you're going to get confused. So then this will be 2 times probability of t greater than absolute value of a negative number will become a positive number, right? So this becomes positive 2.768. Now, this probability is something we can look up the t-table, and the sign is consistent with the t-table, very good. Then we need to know the degree of freedom, which n minus 1, 20 minus 1 is 19. So with 19 degree of freedom, check on the t-score 2.768. The closest neighbor will be 2.539 and 2.861. The corresponding probability for the two neighbors will be 0.01 and 0.005, right? So then the probability of interest will be in between the two probabilities of the neighbors. We put a small probability on the left, a large probability on the right, will be in between those two probabilities. But our p-value is twice as big, so we need to multiply by 2 on this on here. So that will become our p-value. But in order to do that, we need to multiply by 2 on every part of the inequalities, right? So p-value will be between 0.01 and 0.02. So this will be our p-value. So then all the examples basically give us all different possible scenarios of finding p-values from t-table or any kind of situations. And once we're able to find p-values, I mean everything else is exactly the same as the one sample z-test. Okay. So now this is the first animal for the attendance points in this video. This is a red panda. And then we look at an example, right? So here, this is a very similar example from chapter 15, the z-test. But this is a similar example earlier when we do the t comfort interval. So the composition of the Earth's atmosphere may have changed over time. To discover the nature of the atmosphere a long time ago, we can examine the gas and bubbles in sand and amber. Amber is a tree resin has hardened and been trapped in rocks. The gas and bubbles within amber should be a sample of the atmosphere at the time when the amber was formed. Some specimen of the amber from late Cretaceous era, 75 to 90 million years ago, give you the percentage of nitrogen as following. So you have all different nitrogen percentage. Suppose that the observation is a simple random sample from late Cretaceous era, and the nitrogen percentage in amber has a normal distribution. A scientist claims the percent of nitrogen in late Cretaceous era air is lower than that of current air. The current air is 78.1%. Now we need to see if that claim is being true or false. So basically, we need to test if that claim is true or false, right? So even though I tell you to do a t-test, but you need to make sure you understand we're trying to estimate a claim being true or false. That means this will be a test. And then what test do we do? We have two options now, right? We have z or t. That depends on if sigma is given, right? Sigma is not given, right? It's unknown. So that means we need to do a t-test. Okay? So even if I don't tell you to use a t-test, you should know the only test that's appropriate for this problem will be a t-test. Okay? And then once the sample is given to us, we can calculate the mean and standard deviation, just like on the previous example on comfort intervals. The sample mean we can calculate to be 59.6. Sample standard deviation will be 6.26. And the sample size will be, we have 9 numbers, right? We have 9 different values. Okay. So now let's go ahead and do this test. Okay. So we need to have 5-step procedure, right? Don't forget about a 5-step process. So we decided this is a t not comfort interval t-test, because we're trying to assess claim being true or false. Then for any hypothesis test, the first step is stating your hypothesis. We have 2 hypotheses, null and alternative, right? Then let's go back to the question, what is our hypothesis? The hypothesis is the claim, right? The claim says that percentage of nitrogen in late Cretaceous era is lower than current air. This is the claim, right? Then this claim will be our hypothesis. What kind of hypothesis is this? Null or alternative? Is it stating something being the same or different? Lower than, right? Lower than means they're not the same, right? So this claim will be our alternative hypothesis, right? So then let's put in here. Our alternative hypothesis will be the nitrogen percentage in late Cretaceous era is lower than current, and current area is 78.1%. So this is our alternative hypothesis. The null hypothesis will be basically the same as 78.1%. Right? And we can write those sentences using symbols. So if we use mu represent the average nitrogen percentage in late Cretaceous era, then mu will be lower than 78.1. Right? And the null hypothesis will be mu is the same as 78.1. So the first step is done, stating hypothesis. Second step, state the rejection rule. So if P is less than alpha, then reject the null. So the only thing you need to change is what alpha value do we use here? Type 1 error rate, right? So go back to the question. Are we given alpha value? Obviously, we are given 0.01 as the thickness level, right? That's what alpha represents. So here we need to have 0.01. So that's step 2. Step 2 is done. Now we go to step 3, calculating test statistic and find p-value. So you need to realize we're doing a t-test. The test statistic will be a t-statistic. And by definition, t-statistic is x bar minus mu divided by s over square root of n, right? Then we need to find all the values here in order to calculate. We need to find what x bar is, what the mu is, what the s is, and what the n is, right? So then we go back to the question, try to find each of the values that mean x bar, we can calculate s, we can calculate the 59.6 and 6.26, n is 9, right? And now we're going to bring them in to the calculation. Mean is 59.6, s is 6.26, n is 9, right? So we have one little piece here. What is mu? Where do we find mu? When you calculate test statistic, we always need to assume something, right? What do we assume? We assume the null hypothesis is true, right? So the p-value is defined. The probability of observing a sample as extreme or more extreme than the sample reflected, assuming the null hypothesis is true. Okay? So if we assume the null hypothesis is true, then mu will equal to 78.1, right? Then we have everything we need for the calculation. X bar, 59.6. Mu, 78.1. S, 6.26. N is 9. And a little calculation, we can calculate this to be negative 8.86. So the test statistic is calculated. And the step 3 is calculating test statistic and then find p-value, right? So we need to find p-value, just like the practice we did earlier. We need to find p-value. P-value will take different forms depending on your alternative hypothesis, right? For different alternative hypotheses, for the different signs, you're going to have a different p-value expression, right? So just practice. When you have a smaller than sign, the p-value will be probability of p smaller than calculated p. That's definition. Then p-value, probability of t smaller than calculated t. What's calculated t? Calculated t is right here, right? So that will be negative 8.86. So we're going to replace it here. Then this is a t event. We want to look it up on the t table, but we do know t table will require an upper tail probability, which means we need to have a greater than sign here. You have a smaller than sign, we need to convert it, right? So here we're using the symmetry rule, right? the left tail probability will be the same as the right tail probability because they're mirror image. So if we convert it, it will be probability of t greater than positive 8.86, right? Then you have a t event with a greater sign. We can look up the t table. The degree of freedom will be sample size n minus 1. So 9, sample size is 9 minus 1, you have 8. So we're going to check a degree of freedom, then probability of t greater than 8.86 is what we need to look up. So you can realize we're only going to have one neighbor, right, on the t table, a degree of freedom, 5.041 is the only one neighbor we have. And the corresponding probability is 0.0005, right? Then, since you have a bigger t-score, your probability will be smaller, right? Because you're cutting the right tail off. So this probability will be smaller than 0.0005. Right? Then step 3 is done. So basically we find p-value. P-value is less than 0.0005. Then we go to step 4. Apply rejection rule and make a decision. So we're going to apply this rule to make a decision. So now we know what the p-value is. We know what alpha is. If p is less than 0.0005, then it's definitely going to be less than 0.01. Right? Then by the rule, if that's the case, our decision will be we're going to reject the null hypothesis. And the last step is interpretation. We need to write a conclusion. It's the same format as chapter 15 for the z-test. So we're going to conclude, since we reject the null, then we do have enough evidence that after that is alternative hypothesis 2, right? Just write the alternative hypothesis in here in words, that the nitrogen percentage in late Cretaceous era is lower than the current era, which is 78.1%. Right? And it would be nice to say what type 1 error rate it is. So we're using 0.01 significance level. Okay, so this is complete process of one sample test. And again, for any hypothesis test, we have a chance to commit an error, right? We either have a chance to commit a type 1 error, or we have a chance to commit a type 2 error, right? So in this case, what type of error is possible since you reject the null? There will be a chance for a type 1 error, right? So for the decision we made, we're saying the nitrogen percentage for late Cretaceous era is lower than current era. That's our decision. But that will have 1% of chance to be wrong as that decision, right? In any case, we have 99% of chance to be correct, right? So the hypothesis test always helps us to make a better decision based on the chance of being correct or being wrong. We can have much higher chance to be correct for all the decisions we make. And that's how we, utilize hypothesis test to make a better decision. Okay. Right, so this is this problem. Then we can do another practice real quick. So the tribal urban district assessment, TUDA, is a government-sponsored study of student achievement in large urban districts. TUDA gives a reading test score between 0 and 500. It's claimed that the average score for the reading test is 255. One person is questioning that claim. So when he's questioning that claim, he's saying basically he thinks the average score for the reading test is not 255, right? So it could be lower and higher, but he just doesn't believe it's it is. So the person collected a sample of 1,000 eighth graders in Atlanta who took the TUDA test. The sample had a mean of 250 with standard error of 1.8. So here give you a standard error. You need to understand what a standard error means, right? And then perform a t-test with significance level 0.05 and state your conclusion. Okay. So when you look at the problem, so we're doing assessment, right? We want to assess that claim being true or false. So obviously this is a hypothesis test. Is sigma given anywhere? No. Then this has to be a t-test, right? So even though I tell you to use a t-test in this chapter, but by the end of the semester, you need to be able to tell what inference process to be used for each different scenarios. So different inference procedure, just like a tool, you use different tool for a different problem. And we're given, so the claim is right here. The average score for the reading test is 255, right? So this claim will be a hypothesis. Now what kind of hypothesis is this? Is this null hypothesis or alternative hypothesis? Obviously this is a null hypothesis, right? It's stating something being the same, right? The average score is the same as 255, right? Okay. Now we're given some numbers. The 1,000 eighth grader will be our sample, so then 1,000 will be our sample size n, right? Then sample mean is 250, that's our x bar, and then standard error 1.8, that will equal to what? Standard error will equal to standard deviation over square root of n, right? So don't forget that. Then let's work out this problem. So we are doing a t-test, like we mentioned earlier. Then for any hypothesis test, you need to go through the 5-step procedure. So the null hypothesis, basically, just like we indicated earlier, the average score of I don't know why this keeps happening. All right, so average score of all eighth graders, right? You check the question. The population will be the tribal urban district sponsor study and the large urban school districts and the eighth graders in Atlanta, right? So that's our population. So average score of eighth graders in Atlanta is the same as 255, right? And then what's your alternative hypothesis? Basically, everything the same, but here is going to be not the same. Not the same will be different, right? So you write the symbols. Here will be mu is not equal to 255, and here is mu is equal to 255. That's your hypothesis. Second step, state the rejection rule. Same sentence. P is less than an alpha, then reject the null. So we need to know what alpha value we use, right? So in the problem, does it give us alpha? We are told to use 0.05, right? Even if we are not being told, the default value is 0.05 anyway, right? And step 3, calculating test statistic and find p-value. So the test statistic is going to be a t-statistic. The calculation will be x bar minus mu divided by s over square root of n. And now let's check what are we given. Are we given x bar? Are we given mu? Are we given s? Are we given n? And what are we given here? So we're given sample size equal to 1,000. So this is our n. We're given x bar is 250. We're given standard error, which is s over square root of n, will equal to 1.8, right? Then let's bring it back here. That means x bar is 250, mu is 255, s, we don't know, n is 1,000, but it also given s over square root of n as a standard error is 1.8, right? So now we're plugging the numbers in. X bar is 250, mu is 255, and then we don't know s, but we do know s over square root of n as a whole thing. That's our standard error in here, right? So that's 1.8, and we can calculate it, which is negative 2.78. Then we need to find our p-value. The p-value is dependent on your alternative hypothesis, okay? So we have not equal sign, p-value will be equal to 2 times probability of t greater than calculated t's absolute value. And the calculated t is right here, we're bringing it in 2 times probability of t greater than negative 2.78 absolute value. Then get rid of the absolute value function, so 2 times probability of t greater than positive 2.78. So we can evaluate this t event on the t table for the probability with the degree of freedom will equal to n minus 1 is 999, right? So we're going to go to the t table, look for that probability. 999, the closest degree of freedom to approximate will be 1,000 anyway, right? So looking for t-score 2.78, we can see that we can have 2 neighbors on that degree of freedom, 2.581 and 2.813. And then corresponding probability is 0.0025 and 0.005. Okay, I put them in the reverse order. So 0.005, and this is 0.0025. So that means probability of t greater than 2.78 will be between the 2 probabilities here, right? So put the small number on the left by convention, and the large number on the right. But our p-value is not this, right? Our p-value need to be twice as big, right? You multiply by 2, the middle becomes p-value, and here is 0.005, and here is 0.01. So this is our p-value. And step 3 is done, p-value is found, we go to step 4. So now, since p is between 0.005 and 0.01, compared to 0.05, p is going to be smaller than 0.05. Then what's our decision? By the rule, we need to reject the rule. And the last step, write a conclusion. So we have enough evidence that the average score of the 8th graders in Atlanta is different from 255 and based on, 0.05 significance. Okay. So make sure you understand the whole process of hypothesis test. Basically, the big thing is the 5-step procedure. Understand what we're doing in each of the steps. So step one, step one, stating hypothesis. Step two, stating rejection rule. Step three, calculating test statistic find p-value. Step four, apply rejection rule and make decision. And step five, conclusion, interpret the results. Okay. All right, so this is our second animal for this PowerPoint video. This is a gorilla. Okay. And then last, we have a practice for you guys to work on this. In a class, normally I will have students work on this, but this is an online class. I'm going to go ahead and explain this to you. But make sure you understand the process again. Sam pays $740 for his rent, and he wants to see if he pays too much. He asked people who live on the neighborhood with the similar house sizes, and 10 of them will give him their rent amount. It's found out the mean standard deviation of the 10 houses on the neighborhood is $650 and $90 respectively, and we conclude that Sam is overpaid. Okay. So when you look at the problem, we are trying to assess a claim being true or not, right? Is Sam overpaid, true or false, right? Then this will be a hypothesis test. Then let's look at all the information we're given. What is 90? 90 will be the standard deviation of the 10 house, right? Then you need to realize the 10 house will be our sample. The population will be all the houses on the neighborhood, right? Then this 90 will be standard deviation of the sample, so this will be S. And the 650 will be the mean of the sample, which is X4, right? So basically, there's nowhere given us information about sigma. Then this should be a t-test, right? Right. So then, let's work on this. So we know we need to do a t-test. Then all the hypothesis tests will go through the 5-step process. First step, stating hypothesis. Then the claim we're evaluating is Sam is overpaid. Overpaying than everyone else in the neighborhood, right? Okay. So the term hypothesis will be Sam pays more than all people in neighborhood. And basically this is an average of all people in neighborhood, right? And then the null hypothesis will be Sam pays the same as average of all people in neighborhood. Right? So now how do we write this in symbols? So here is a little trick, don't get confused. So the average of, this is your population. All the people in the neighborhood is your population. And the 10 person that Sam asked is the sample, right? So the average population is mu. Then how much does Sam pay? We already know how much Sam pays. Sam pays 740, right? Then what are we trying to see? We're trying to see if Sam pays more than everyone else. So the relationship will be this, right? So then if you write it out, actually going to be mu is smaller than 740. right? Sam pays more than average of the population. And the null hypothesis is Sam pays the same as everyone else in the population. Right? All right, so don't get confused. Write the words out and then convert it to the symbol so that you don't get the sign wrong. Okay. So second step, state the rejection rule. If p is less than alpha, then reject the null. So we just need to know what alpha to use, right? So let's check on the problem. Does it tell us what alpha to use? Apparently it didn't, right? But we know if we're not given alpha, we have a default. The default alpha will be 0.05. Then step 2 is done. Always the easy sentence. Excuse me. Step 3, calculating test statistic and find p-value. So this is a t-test. The test statistic will be a t-statistic. The calculation will be x bar minus mu divided by s over square root of n. So we need to find all the information corresponding to the calculation here. So we can get a mu right away because we always need to assume the null hypothesis is true, right? Mu is 740. Now let's look at the other statistic we need to know. So we just looked at S is 90, X bar is 650, and N is basically sample size N is here, right? You have 10, right? Then we put into the calculation here. X bar is 650, S is 90, N is 10. We calculate it. That would be 650 minus 740. S is 90, square root of N is 10, and we can calculate this out, right? If you calculate it correctly, this will be negative 3.16. So the test statistics calculated. Now we need to find p-value. P-value will depend on your alternative hypothesis or the sign, right? We have a smaller than sign on alternative hypothesis. P-value will be probability of p smaller than calculated p. So realize this is a t-test. This should be a t event instead of a z event, right? So don't get confused. And then calculate the t, bring it in. That'll be probability of p smaller than negative 3.16, right? Then this is a t event. We want to look it up in the t table, but we need to make sure it's consistent. That means we need to have a greater than sign. So we can change it using the symmetry rule. We're going to change the sign from smaller than to greater than and from negative to positive, right? So then this is consistent with the t table. We can look it up. We need to know what's the degree of freedom we have here. The degree of freedom for one sample problem is n minus 1. N is 10 minus 1 is 9. So we look at 9 degree of freedom. Check for 3.16. That will be between 2.821 and 3.250. The corresponding probability of each of the neighbor is 0.01 and 0.005, right? So we can say that the p-value we're looking for is the same as this probability. It will be between 0.005 and 0.01. Okay? So step 3 is done. We find p-value. Now we go to step 4. So we're going to compare p-value and alpha. P is a number between 0.005 and 0.01. It's definitely going to be smaller than 0.05. Now we go back to the rule. If that's the case, then we need to reject the null. So now the last step, we need to write a conclusion. We're going to say we have enough evidence that Sam pays more than average of the whole neighborhood, right? So that means we have enough evidence that Sam pays more. That means Sam is overpaid. And this conclusion is based on 0.05 type 1 error rate or significance level. So that means we have 5% chance that our statement is wrong. Right? But we have 95% chance that the statement is correct. Right. So then this is it for one sample t-test. Okay. We have 2 more hypothesis tests to cover. They're all going to use the 5-step process, so make sure you understand the process. All right, so we're going to stop here. Let me know if there are any questions.